9.2 Valence shell electron pair repulsion theory, VESPER. The best arrangement of a given number of electron domains is the one that minimizes the repulsions among them. Electron domain geometries. These are the electron domain geometries for 2 through 6 electron domains around a central atom. They are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. All one must do is count the number of electron domains in the Lewis structure. The geometry will be that which corresponds to the number of electron domains. The electron domain geometry is often not the shape of the molecule, however. The molecular geometry is that defined by the positions of only the atoms in the molecules, not the non-bonding pairs. In this example, we have ammonia. Ammonia has 3 bonded pair and 1 lone pair, giving it 4 electron domains. Because it has 4 electron domains, the electron domain geometry is called tetrahedral. However, the molecular geometry is trigonal pyramidal. Within each electron domain, then, there might be more than one molecular geometry. So if we're looking at tetrahedral, we could have tetrahedral, we could have trigonal pyramidal, as in the case of the ammonia molecule where there's 1 lone pair, or we could have bent if there were 2 lone pair and 2 bonded pair. In the linear domain, there is only one molecular geometry, and that is linear. Note, if there are only 2 atoms in the molecule will be linear no matter what the electron domain is. There are 2 molecular geometries, trigonal planar if all the electron domains are bonding, and bent if one of the domains is a non-bonding pair. Again, this is trigonal planar electron domain. We can have trigonal planar electron domain. It can have a molecular geometry of either trigonal planar or it could be bent as well. Sample exercise 9.1 using the VESPER model. Use the VESPER model to predict the molecular geometries of O3 and SnCl3-. We are given the molecular formulas of a molecule and a polyatomic ion, both conforming to the general formula ABN, and both having a central atom from the P block of the periodic table. To predict the molecular geometries of these species, first we draw their Lewis structures and then count the number of electron domains around the central atom. The number of electron domains gives the electron domain geometry. We then obtain the molecular geometry from the arrangement of the domains that are due to bonds. We can draw 2 resonance structures for O3. Because of resonance, the bonds between the central oxygen atom and the outer oxygen atoms are of equal length. In both resonance structures, the central oxygen atom is bonded to the 2 outer oxygen atoms and has 1 non-bonding pair. Thus, there are 3 electron domains about the central oxygen atom. Remember that a double bond counts as a single electron domain. The arrangement of 3 electron domains is trigonal planar. 2 of the domains are from bonds, and 1 is due to a non-bonding pair, so the molecule has a bent shape with an ideal bond angle of 120 degrees. As this example illustrates, when a molecule exhibits resonance, any one of the resonance structures can be used to predict the molecular geometry. B. The Lewis structure for SnCl3- ion is as shown. The central tin atom is bonded to 3 chlorine atoms and has 1 non-bonding pair. Therefore, the tin atom has 4 electron domains around it. The resulting electron geometry is called tetrahedral, with one of the corners occupied by a non-bonding pair of electrons. The molecular geometry is therefore trigonal pyramidal, like that of ammonia. Practice exercise. Predict the electron domain geometry and the molecular geometry for these. Non-bonding pairs and bond angle. Non-bonding pairs are physically larger than bonding pairs. Therefore, their repulsions are greater. This tends to decrease bond angles in a molecule. So if we look at the tetrahedral electron domain geometry, we see that a bond angle of 109.5 is normal for something like CH4. However, for ammonia, NH3, there is a lone pair that takes up more space, and the bond angle has been decreased to 107. In a water molecule, which also has a tetrahedral electron domain geometry, but is bent, has a molecular geometry of being bent, the two lone pairs take up even more space and squeeze those hydrogens to a 104.5 degree bond angle. Multiple bonds and bond angles. Double and triple bonds place greater electron density on one side of the central atom than do single bonds. Therefore, they also affect bond angles. In this example, we see that the bond angle between the chlorine and the double bonded oxygen is 124.3 degrees, whereas the bond angle between the two chlorines is only 111.4. Tetrahedral electron domain. There are three molecular geometries. Tetrahedral if all are bonding pairs, trigonal pyramidal if one is a non-bonding pair, and bent if there are two non-bonding pairs. Trigonal bipyramidal electron domain. There are two distinct positions in this geometry. They are axial and equatorial. Lower energy conformations result from having non-bonding electron pairs in equatorial rather than axial positions in this geometry. There are four distinct molecular geometries in trigonal bipyramidal electron domains. They are trigonal bipyramidal, seesaw, T-shaped, and linear. Octahedral electron domains. All positions are equivalent in an octahedral domain. There are three molecular geometries: octahedral, square pyramidal, and square planar. Sample exercise 9.2, molecular geometries of molecules with expanded valence shells. Use the VSEPR model to predict the molecular geometry of SF4 and IF5. The molecules are of the ABN type, with a central atom from the P block of the periodic table. We can predict their structures by first drawing Lewis structures and then using the VSEPR model to determine the electron domain geometry and molecular geometry. The Lewis structure for SF4 has been drawn. The sulfur has 5 electron domains around it, 4 from the SF bonds and 1 from a non-bonding pair. Each domain points toward a vertex of a trigonal bipyramid. The domain from the non-bonding pair will point toward an equatorial position. The 4 bonds point toward the remaining 4 positions, resulting in a molecular geometry that is described as seesaw-shaped. The experimentally observed structure is shown on the right. We can infer that the non-bonding electron domain occupies an equatorial position as predicted. The axial and equatorial SF bonds are slightly bent back away from the non-bonding domain, suggesting that the bonding domains are pushed by the non-bonding domain, which is larger and has greater repulsion. So again, in this picture, we can see that instead of 180 degrees, this is actually a little bit smaller, or a little bit different. It's 186. So these are being pushed away from the non-bonding pair, which is over here. B, the Lewis structure of IF5 is drawn. The iodine has 6 electron domains around it, one of which is from a non-bonding pair. The electron domain geometry is therefore octahedral, with one position occupied by the non-bonding pair. The resulting molecular geometry is therefore square pyramidal. Because the domain for the non-bonding pair is larger than the other domains, the 4F atoms in the base of the pyramid are tipped up slightly toward the fluorine atom on top. Experimentally, we find that the angle between the base and the top fluorine is 82 degrees, which is smaller than the ideal 90-degree angle of an octahedron. Remember that all the positions in an octahedral are the same. So we don't have to choose between an axial position and an equatorial position. For practice, predict the electron domain geometry and molecular geometry of these two examples. Larger molecules. In larger molecules, it makes more sense to talk about the geometry about a particular atom rather than the geometry of the molecule as a whole. In this example, we can examine each of the atoms along the chain. We see that this carbon atom has 4 domains and has a tetrahedral electron geometry. This carbon has 3 domains and therefore has a trigonal planar electron domain geometry. And this oxygen has 1, 2, 3, 4 electron domains, making it tetrahedral. The actual molecular geometry here, however, is bent. This approach makes sense, especially because larger molecules tend to react at a particular site in the molecule. For instance, this molecule might react here with another organic compound. Sample exercise 9.3, predicting bond angles. Eye drops for dry eyes usually contain a water-soluble polymer called polyvinyl alcohol, which is based on the unstable organic molecule called vinyl alcohol. Predict the approximate values of the HOC and OCC bond angles in vinyl alcohol. We're given a molecular structure and asked to determine 2 bond angles in the structure. To predict a particular bond angle, we consider the middle atom of the angle and determine the number of electron domains surrounding that atom. The ideal angle corresponds to the electron domain geometry around the atom. The angle will be compressed somewhat by non-bonding electrons or multiple bonds. For the HOC bond angle, the middle oxygen atom has 4 electron domains, 2 bonding and 2 non-bonding. The electron domain geometry around the oxygen, therefore, is tetrahedral, which gives an ideal angle of 109.5 degrees. The HOC angle will be compressed somewhat by the non-bonding pairs, so we expect this angle to be slightly less than 109.5. To predict the OCC bond angle, we must examine the leftmost carbon atom, which is the central atom for this angle. There are 3 atoms bonded to this carbon atom, 1, 2, 3, and no non-bonding pairs. And so it has 3 electron domains about it. And the predicted electron domain geometry is trigonal planar. So we have 1, 2, 3 domains. This carbon is trigonal planar, resulting in an ideal bond angle of 120 degrees. Because of the larger size of the carbon-to-carbon double bond, however, the OCC bond angle should be slightly greater than 120 degrees. Practice exercise. Predict the HCH and CCC bond angles in the following molecule called propyne.